All right, so in this video, we're gonna go through a lot of examples. I'm gonna use just these two curves, and we're gonna compute the volume that we obtain by revolving around the x-axis, around the y-axis, and then at some point when I revolve it around the line, maybe y equals 1, x equals 1, and then y equals 1. We could do -1 as well. We'll decide as we go. So this video is going to be a little bit long. We're going to do a lot of these calculations, but hopefully it elucidates how to use these methods, shell method, washer method, or whatever you want to call them. The ideas are the same, so we're going to work on them, and we're going to start with revolving around, for example, the x-axis. Okay, so when we rotate this region around the x-axis, it'll form a figure kind of like this one. And so to compute the volume, what we're going to do, I'm going to start at an x. Let's start with the same color. Excuse me. We're going to start at an x. We're going to pick a rectangle of infinitesimally thin rectangle. So the width of this is going to be a dx. Now, notice what happens to it when I rotate it around. This whole space is going to be open, and this here is going to be going around like this. And then you're going to have the thickness of the rectangle is going to give you a thin shell, or a thin washer rather. And so that washer is going to look like this. So you're going to have a big radius and a smaller radius, and there's going to be your infinitesimal thickness to it. Now that thickness is going to be your dx, because that is the thickness that you rotate it around. So this is going to be, your thickness is going to be here, let's say. All right, so that shell has two radii. The first one is a small one, so it's going to go from the axis up to the first curve. That's going to be your radius. I'm going to call it little r. And so that's going to be the radius that's going to be located right here. And that is little r. That's going to be your radius. Then you're going to have a bigger radius, which is going to be from the axis up to the larger curve. That's going to be given here. Going to be capital R. So for us, the larger radius, let's look at it here, is when you go from the 0 to the curve square root of x. So that's going to be, the larger radius is going to be square root of x. The smaller radius is when you go from the axis up to the first curve, which is going to be x squared. Now, what is the volume of this little washer? Well, it's going to be the volume of the big disk minus the volume of the smaller disk. Okay, so what is the volume of the big disk? Well, the big disk is going to be pi r squared, and the small disk is the area, or the volume rather, is going to be pi little r squared. Everything multiplied times dx, because those were the areas of each of the faces of the disk. Then times its thickness is going to give you your dv. All right, so now this is going to be our formula for what they call the washer method. I don't like calling it anything, but would be the volume between the integral between a and b rather of pi multiplied here of the big radius, they call it r of x, and that's a square, a little too excited there, minus little r dx. I rather draw it and see it than actually writing a formula for it, because the formula tends to lead you to mistakes if you just apply it and you're not judicious about it. But in our case, then the volume becomes pi times the integral from 0 to 1, 0 to 1 because that's where we're going on the x-axis, 0 to 1. And then capital R we said was square root of x square root of x squared minus little r we said was x squared. Sorry, yeah, x squared, and then squared dx. And so at this point you just have that this is going to be pi integral from 0 to 1 of x minus x to the fourth dx. And we don't have room, but we can compute this quickly. It's going to be x squared over 2, so it's going to give us the integral will be 1/2. And the other one is going to be minus 1/5. So that's going to be 5 minus 2, 3/10. Sorry, I rushed the math there, but we had no room left. But what I want you to understand is the concept. This part you already know how to do. And if you're not comfortable with it, you can go back to our videos on the fundamental theorem of calculus. So you can do that. All right, so that's rotating around the x-axis. So we ended up with a washer. Could you use the shell method? Of course, but just use the one that is the most natural. So let's go ahead and rotate around the y-axis where we're gonna get a shell. All right, so let's do that. So here we're gonna rotate around we rotated rather around the y-axis, and we obtained this figure here. So if we pick x here, and we have a rectangle with a differential of thickness, we rotate it around. Let's draw it with this color and see how it goes. Oh, this weird. So you end up with that type of shell. So that's going to be what is called as a shell. What is it known as a shell rather? And it's more of a cylinder, but the difference is the real difference is that the thickness, the infinitesimal thickness, happens here. In the other case, it was the thickness of our washer. Here is the thickness of this shell. So the volume of this is going to be computed differently. So this thickness is going to be our dx. All right, so to compute the volume of this, what we're going to do is we're going to cut it, as I said in the other video. I have another video on this. So you cut it out and you split it, and or straighten it out, if you will, and you're going to end up with a rectangular face and a differential of thickness dx there. Now this part here would be the circumference of this shell. And if we call that radius r, then this would just be 2 pi r. And now what is the, and for us, by the way, that radius is just going to be this x value. 3 x's there. I guess I really wanted to write x. Oh well. So this is going to be 2 pi x. All right, now the interesting one is the height of this. The height here would be just this y minus this y. That would be my height. And what is the top? So if you look at this one, the top function is going to be your square root of x. So that's going to be just square root of x minus the bottom one, which is x squared. That's going to be the height of this shell here. All right, so that corresponds to this right here. Okay, so now when you want to compute the volume of this, the dV is going to be base times height, if you will, times the thickness. So you're going to have 2 pi r, which is 2 pi x, times this one right here, which is square root of x, minus x squared, all of it times dx. So now to compute the volume, I just have to integrate my 2 pi r. Oh, by the way, integrate where? Well, I'm still taking my my x's, or my rectangles, perpendicular to the x-axis. So I'm going to have the interval for the x are on the x-axis, and on the x-axis I go from 0 to 1. In this particular example is the same for y, but I'm telling you that you are doing your integral with respect to x, so you're going to look at your endpoints on dx. If you had a dy, you look here. If you have a dx, you look here. All right, so we have from 0 to 1, 2 pi, and let me distribute this x. So I get x to 1/2 times x is going to be x to 1/2 plus 1, which is 3/2, minus x cubed dx. All right, so let's go ahead and compute this. So we're going to have 2 pi. Now the integral of this one is going to be 3/2 plus 1 is 5/2. So it's going to be 2/5 x to 5/2. Remember, I multiply times the reciprocal instead of dividing by 5/2. And then this is going to be plus 1 x to the 4th over 4. All of it between 0 and 1. And I get 2 pi. And when I evaluate, I just have to evaluate everything at 1, because I don't get anything when I evaluate it at 0. So minus 1/4. That's going to be common denominator is 20, so I get 8 minus 5, so 3/20, and the 2's cancel, and I get 3 pi tenths. So it's the same figure that I had obtained when I rotated around the x-axis. I got the same one when I rotated around the y. So right, a little bit off scale, but I'm going to rotate it around here just to see how or what it looks like. All right, so I'll draw it, and I'll see you back here when it's all drawn out. All right, so if we rotate around this line, you grab this and go around, you're going to form something that looks sort of like this. My drawing, it took me a minute, it's not perfect, so forgive me for that. Not a great, wouldn't have made it as an artist, let's put it that way. All right, so what we're going to do is we're going to grab an x, and that's going to give us a little rectangle here that when I rotate around, I'm going to just do a line. Just imagine the thickness I'm rotating around, just to make it a little bit less cluttered. So I'm going to be rotating that line around. Oh, vertical stops there. So you're going to rotate it around, and that's going to give you your shell there. Actually, let's make it solid so we see the shell. So that would be your shell in there. And that shell again has an infinitesimal thickness. And we need to figure out now the radius. The radius is not just x as we did in the previous example. It is going to be a little bit different because I have x right here. And so this distance is going to be the distance between x and 2, because I'm going, the center of my circle here is 2, where I'm rotating things around. So I'm going to be going, since x is less than 2, this distance is going to be 2 minus x, because I go all the way to 2, that's this big distance, minus this distance gives me this. Did that make sense? It's just going to be 2 minus x is going to give me the remainder, which is the distance, which is the radius. So that radius here is going to be 2 minus x. That's that one. And now the height is going to be just as before. The height is not different from the previous example, but that radius did change. So this distance is again going to be the distance here, which is from the square root of x to x squared. So that one didn't change. And again, imagine I cut it out, split it, or open it up. This gives us that the volume of that dv is 2 pi r. 2 pi r, it gives you the circumference. And r in this case is 2 minus x. That's going to give me 2 pi r, the circumference. That's going to be the base of my rectangle as I drew it in the previous example, times this height times the dx. Whew, barely fit it there. All right, so now it's a matter of FOILing this out and integrating from 0 to 1. So v is going to be 2 pi, the integral from 0 to 1, and let's FOIL this out. So I'm going to have 2 root of x minus x to 3/2, and then I'm going to have minus 2x squared, and then that was plus, minus x, that the plus was the x cubed, that was still minus. Fail. So minus 2x squared, and I'm missing the last one, plus x cubed. All right, so now it's a matter of integrating that. Sorry about the mess, I just didn't have room to write it all out. All right, so let's go ahead and integrate. And so we get that the volume then is going to be 2 pi integral, or just calculate it. This is going to be x to 1/2. When you add a 1, it's going to be x to 3/2. And so it's going to be 2/3 times 2, 4/3, and then x to 3/2. Now this one is going to be 5 x to 5/2. And that's going to be 2/5 then, the reciprocal, x to 5/2. And then this one is easy. So 2/3 x cubed. Lastly, plus 1/4 x to the 4th. All of it evaluated between 0 and 1. So integrate, and now evaluate from 0 to 1. But notice that since I'm going from 0 to 1, and all of these are 0 when x is equal to 0, and they're 1 whenever I evaluate each one of them at 1, I'm going to have 2 pi, and then just the coefficients. So 4/3 minus 2/5 minus 2/3. I could have just written that as 2/3 here. Let's do that. Collect at least one term. So 2/3 minus 2/5 plus 1/4. And that will give you your volume. All right, so now if we rotate around the line y equals 1, we get a figure that looks a lot like the ones we got before. We'll see what the volume ends up being. Maybe the same. All right, so this one, you can go ahead and pick an x. And if you pick a rectangle, I'm going to draw it just as a line. Then when you rotate it around, there's nothing in here. When you rotate it around, that is going to generate a little shell in there. It's a little crooked. We're not going to sweat it. We're going to draw the shell here. And the thickness is going to be a dx, because I'm still doing everything with respect to the x, or x variable, so I'm taking everything perpendicular to the x. I could have, by the way, just to let you know, I could have gotten, if I grab something in this direction, I would have a dy, and I would have to rotate it here, giving me a shell if I rotate it in this direction. So it's just simple to do it here in the x. You can do it with respect to y. There's times when you cannot solve a function in terms of the one of the variables, but it's in terms of the other, or it's easy to integrate with respect to one of the variables and not with respect to the other. Then that's when you would favor either doing it with x or y's. That really is, it boils down just to that. But the procedure is the same in any event. All right, so now the radius, that's what matters here. We have two radii, the small one and the large one. So let's take a look at first at the small one. I'm going from 1 to this direction here, to this y. What is the y that goes on top? Is the square root of x. So the small radius, let's call it r. R is going to be equal to 1, that's the distance here, to the larger one. So it's just this distance here. So 1 minus the large one is the square root of x. Now, when I go to the large radius, that radius here is going to be 1 minus the bottom one. It's going to be this big radius here, from here down to here. That's my big radius. And that's going to be 1 minus the bottom function. The bottom function is the square root of x. So r is going to be 1 minus, I said square root, the square of x, sorry. I think I said square root, but it's just the square, the bottom function. Okay? So that's that. So then now we have to compute the volume of that washer. And that is just going to be the volume of the big disk, which is pi r squared dx, capital R, minus the small one, all of it dx. And now I just plug it in and I integrate. So I integrate from 0 to 1 because I'm, again, going from 0 to 1. We rotated that region in every possible direction, I think. And then pi, I'm going to factor that one out, just put it out. Pi, now capital R is 1 minus x squared minus r squared, 1 minus square root of x squared dx. All right, so we have to do a little bit of algebra because we have to FOIL things out. So let's go ahead and do that. So when we FOIL here, I'm going to have a 1 minus a 1 that's going to be gone. So I'm going to have the square of the second is going to be x squared minus 2x. So technically it would be 1 minus 2x plus x squared, but my 1 is going to cancel here, so I'm going to not write it out. Sorry about that. All right, so now here I'm going to have minus, again, the 1 went away. When I square this one, I just get x, and then minus the double product, but I have a minus outside, so plus 2 square root of x. I know I summarized that algebra a lot, but I don't have a lot of space, and I know you guys know how to do that. Or do you? I hope so. Now you do. All right, so now here I get x squared minus 3x plus 2 square root of x. I can now integrate, so I'm going to have pi x cubed over 3. That's that one. Now this one's going to be minus 3/2 of x squared. I'm going to have to continue down here, and this is going to be an x2 1/2 plus 1 is going to be x2 3/2, and so it's going to be 2/3, so plus 4/3 x2 3/2. All of it between 0 and 1. Again, in this case, when I evaluate at 0, everything cancels out, so it will boil down to just the coefficients, because when I evaluate at 1, I just get the coefficients. So evaluating, I get 1/3 minus 3/2 plus 4/3. So that's going to be 5/3 minus 3/2, and that's going to give us, I'll compute it here, let's see. So I'm getting pi over 6. Again, if I did the arithmetic wrong, I'm going to post the right answer. But that should illustrate all of the different scenarios you're going to encounter with both the shell, washer, and washer is just a special case, or the disk is just a special case of the washer. So it's the same idea. So I hope this made sense. I hope this helped understand the differences between the methods and how they work. All right, so that will conclude this video. Thank you for watching.